I wanted to go through the slides which define the features of a wave. To begin with, let's define some parts of a wave. The top and the bottom of the wave, what we would call peaks maybe. The top would be a crest and the bottom would be a trough, especially if you're thinking about ocean waves. And remember this word T-R-O-U-G-H is pronounced trough. Go figure on the English language. And wavelength. Wavelength is the distance for one whole back and forth motion, one whole wave. So here we see it is the crest to crest, the top of the wave to the top of the wave. It could also be the trough to the trough. It's the same distance. Be careful if you look at the middle of the wave. If you go from one place that the wave crosses the center, that dotted line, to the next, that's only half of the complete wave because it's gone up and back down. Now it has to go down and back up. So you could go from where it crosses going up to the next place it crosses going up over here. Now here we see trough to trough. The period, the time for one whole back and forth motion. In other words, when you're looking at the simulation, the time it takes this piston to go up and down one complete cycle. Another way to look at it is how long it might take a wave to pass from one crest to the next crest, past some fixed point, like this dotted line. The frequency, how many whole waves pass in 1 second. So if we were standing at this window, say, and these waves are traveling out the window, how many peaks, how many crests pass out the window as we stand and watch in 1 second? The wave speed is how fast the wave is moving through the medium. Remember, waves are energy. So it's sort of how fast the energy is moving through the medium, but the wave. The distance it travels divided by the time it takes. So if this peak in the middle takes 2 seconds to go 6 centimeters, we could set it up 6 centimeters is the distance divided by 2 seconds. 6 divided by 2 is 3. That wave would be going 3 centimeters per second. Amplitude, how much displacement a wave causes. This is how far the wave travels from its center line. So remember, we're not talking about the wave going out the window. We're talking about how far the rope is deformed from what it would be if there were no wave in it. That yellow dotted line down the middle. So the amplitude is from the middle, from the dotted line, to a crest or to a trough. They should be the same distance either way. The direction of wave propagation. This is the direction the wave is going. So in our simulation, the wave starts at the left side of your screen and travels to the right and goes out the window. So the direction of wave propagation is to the right, as this arrow shows. Direction of oscillation. It's the way the wave is wiggling. So, this wave, it may be traveling out the window, but it's been deformed, distorted up and down. So the direction of oscillation is up and down. This wave is making this rope move up and down. So it's oscillating up and down. Here we have our first sighting of 2 different kinds of waves. We have something called longitudinal waves and transverse waves. The transverse wave, as we see on the bottom, is very similar to our simulation. The wiggles, as we just found, are perpendicular to travel. In other words, the direction of oscillation is perpendicular to the direction of propagation. This is the kind of wave you would ordinarily see in a rope that you are waving as the rope was stretched out. Now, longitudinal waves, they're like how sound waves exist, for example. And here we have the direction of oscillation is the same as the direction of propagation. So it wiggles from left to right. It also travels from left to right. So here's another example of a transverse wave. The motion of the particles is perpendicular to the wave direction. There are crests, the tops, and troughs, the bottoms. Here's another example of a longitudinal wave. This would be kind of representative of what sound would look like if you could see the individual molecules of air. There are no crests and troughs in the classic sense. Now notice these sections of density move from left to right, but the particles themselves, and you can see this in the red particles, they don't actually move with the wave. They kind of wiggle back and forth. In other words, the direction of oscillation is left and right, and the wave is traveling from left to right. Here's another example of this. We call these regions of high density compressions. Here we have compressions. And we call the regions of low density rarefactions. So the air is compressed in the compressions, and it's rarefied, which is a way of saying it's less dense in the rarefactions. And we can see here the particle is just going back and forth, left and right, but the wave travels not back and forth, but from the left to the right, right off of the screen. And we get to compare the two. Ocean waves. Now, of course, a lot of us, when we think of a wave, we might think of the ocean or the, going to the beach or something like that. Those are common waves for us to see in our lives. And they have an interesting way of forming. Notice, again, the particles of the ocean, the water doesn't travel from left to right, but the wave travels from left to right. And you'll notice at the very surface of the water, that particle of water, like if you threw a buoy or something out there and it was floating in the water, it would actually travel in a circle. And then as we go down below the water, the wave quality diminishes, but the particles are still traveling in a circle. It's just a smaller circle. And if you've ever swum in the ocean, in the waves, you would find that the deeper you go, the less you feel the waves. And this is just a few feet. So down here, these particles are barely moving at all. So if you dove down below the waves, you might not feel anything. As you come to the surface, of course, you're floating in a boat, or you're just floating on the surface, you'd be bobbing up and down. We think about earthquakes out here a little bit. It is that sort of a little bit of a threat that we have here. The earthquakes are a form of wave that travels through solid. We hope the Earth is solid anyway. And they have some transverse and some longitudinal properties. So the ocean waves at the surface being transverse, they were circular, but these are like oval shaped. The particles move up and down and back and forth. Here we have, well, we're going to learn more about this. This is a form of resonance in a chamber. But here we might have, it's going to be hard to explain perhaps. You'll see that where my mouse is here, we have a region that becomes dense and then rarefied, compressed, rarefied, compressed, rarefied. And so we see the pressure goes up and the pressure goes down, up and down. I'm looking directly below that spot. But you'll notice the particles at that point, they don't actually move very much. They're kind of staying stationary. It's the particles that are further away that travel the most. So if we look over here, we have particles moving a lot, but this region doesn't really change density as much. So here we see left-right motion of the particles, but the pressure stays relatively constant. You come over here, again with this red particle here, it's not really moving at all, but everything around it's compressing in on it, releasing it, compressing in on it, releasing it, compressing in on it, releasing it, compressing in on it, releasing it. We'll learn more about this later. If you've done the tinkering of the wave, you should find that the wave speed is not related to the amplitude, frequency, or the wavelength. Waves travel the same rate through a medium no matter what the amplitude, frequency, or wavelength is. So the relationship between wave speed and amplitude or frequency or wavelength is constant. If you recall our patterns in the classroom. However, wave speed does depend on tension, as you should have found or will find. Think about it. The more tension you have in a rope, the more the rope wants to return to its equilibrium, to its center point, to its center line. And so it's going to more quickly, as you snap it, that spot is going to more quickly try to return to the center line. That wave's going to have to travel more quickly down the rope in order for the rope to return back to its center line as quickly as it can. And then this slide has a lot on it. We're going to talk about wavelength and wave velocity and frequency here. Remember, wavelength, the length of the wave, and frequency is how often the wave passes by in a second or forms in a second. So there's an inverse correlation between wavelength and frequency, but they're closely connected. You can find the wavelength if you know the frequency and the wave velocity, or you can find the velocity if you know the wavelength and frequency. You can find any one of these three if you know the other two. These three equations here are all just different variations on the same equation. We're solving for velocity, wavelength, and frequency. And remember, when in an inverse relationship, when frequency doubles, wavelength is cut in half.